So last time we defined what we meant by a group action, and so this time we're going to look at two important concepts in group theory, namely the orbits and the stabilizers, so that we can eventually state and prove the orbit-stabiliser theorem, and that's something that we'll eventually use to classify the symmetry groups of the Platonic solids. So let's start by looking at orbits. So orbits. And the first thing that I want to do is I want to let x be an element in the set X. So let x be an element in the set X, and I want G to be a group acting on the set X. And if you can't remember what I meant by a group action, then I highly recommend you watch the previous video. So let G be a group acting on the set X. So acting on X. So here's my definition of an orbit. So an orbit, which I'll write as orb X, so the orbit of X under G, which I write as orb X, is the set of all possible destinations of X under G. So in other words, that's the set of all Gx where G is in G. So that's the definition of an orbit. It's quite simple and straightforward, and it's best illustrated by an example. So let's draw a triangle. And we know that a triangle's got three vertices. So let's say we've got three vertices of this triangle, and let's arbitrarily label this vertex as X. Okay, so X is the corner of this triangle. Now I'm also going to say that G, little g, represents a rotation by 120 degrees in the clockwise direction, like so. And then by doing this we can send X to three different places. So we could keep X the same, we could send X here, or send X here. So let's write that down. So if I apply G once, what I get is the following. So if I rotate this triangle by 120 degrees in the clockwise direction, X goes here. If I apply G twice, so that's G squared, so like this, then X moves over here. And if I apply G a third time, so G cubed, which is just the identity map, because rotating 3 times by 120 degrees is a rotation by 360 degrees, which keeps it the same, then I end up with exactly the same configuration. So X is here. So under this rotation, which I've defined as G, we've got three different configurations of this triangle. So the orbit of X under G is just these three different configurations, and since the size of the orbit of X under G is 3.